it's the metal one. There we go. Now we have sound. All right. Okay. So think of it as a log flume. Think of it as a log flume ride. Okay. The part of the fun is that you might get wet. Okay. Here we go. Are we ready for this? Are you guys ready? I don't think we talked about the F word last week. Let's talk about it right now. Okay. Whoa! Well, I don't usually swing it this way. I think I usually swing it the other way. Right now, if you were a little ant living on this plate next to the cup of water, you'd be using the F word, yes? Right? You'd be using, I better stop here. A little applause for this. You would say, centrifugal force is keeping the water from falling out of the cup, yes? And the cup from falling off the plate. Centrifugal force is keeping me from falling off the plate, yes? Okay, so centrifugal force, the F word, is the notion that when you're in a rotating frame of reference, that there is this force pushing you to the outside, okay? But there's another explanation, and we will use that other explanation, okay, as soon as I plug in my wireless microphone. Try plugging that microphone thing in now. There we go. All right. And then just zoom it so that we can just get sort of like the whole whiteboard in. Okay? And then you can turn the viewfinder toward me, and we'll be good. Okay. So there's another way. There's another way to explain why the water stayed in the cup, why the cup stayed on the plate, why if there had been an ant sitting next to that cup, why the ant would have stayed right there, still using the F word, right? Okay, and the reason is that there is a way with linear, I did that with centripetal acceleration, but there is a way with linear acceleration to make an object stay on the bottom of my hand, and I can show you this, watch. Oops, let's try that again. Dang it. It was working, to be honest, before class I was getting it to work. Oh, I remember what it was. I had to move this hand. I had to make this hand move. So how do I make it move?
Like this.
Make it move down, okay. Oops, that's still not working. I'm moving it down. How should I move it down?
At 9.81 meters per second.
Fast? Just move it fast?
9.81.
Still going faster than me. Yeah, I need to actually accelerate it down, don't I? And if I accelerate it down at exactly 9.81, okay, then basically the fact that my hand is next to the styrofoam, foam rubber apple, okay, next to the object, right, the fact that it's next to it is just happenstance. Okay, if I'm accelerating down, we just both happen to be accelerating down at 9.81. But if I accelerate down faster than 9.81, here we go, right? Okay, I can actually generate quite a lot of force between this apple and my hand, yes? Okay, so I can, like that, yeah? Okay, so the thing that was keeping, we don't have to use the F word, right? Okay, the thing that was keeping my hand, I'm sorry, the cup in contact with the plate, keeping the water in contact with the plate and the cup, right, is just acceleration. So let's just draw a circle. And that's a pretty good circle. That's a pretty good circle. Okay? Okay. Basically, if the water stayed in the cup, if the ant stays on the plate, etc., right? The rule is that at the top, the acceleration, okay, has to be greater than, maybe equal to 9.81 for the water to stay in the cup. So this is concept 0, okay? Is that in order for the water to stay in the cup, you've got to have an acceleration of at least 9.81 meters per second squared at the top. Okay, now, having said that, if I actually am spinning it so that it is exactly 9.81 meters per second squared, and remember, this is a centripetal acceleration. So the object is actually moving, say, that direction, but which way is it accelerating? It's accelerating toward the center, correct? Right? So this centripetal acceleration is down. If it happens to be that at the top, that your centripetal acceleration is 9.81 meters per second squared, then basically the water is weightless for one instant in time, right? At that instant, at the very top, right, it's exactly weightless. So I can take this thing, I can spin this, and if I spin it really fast, there's a lot of tension at the top, right? But if I slow it down, right when the string goes slack at the top, like right there, right? There's some minimum speed, and at that minimum speed, if you were riding on that ride, you would actually feel weightless at that instant at the top. Yeah? Can I use the F word to explain why?
Yeah, sure.
Yeah, okay. Here's why. Because at the top, you would feel a centrifugal force up of 1g, but that would be exactly counteracted by gravity, which would be a force downward of 1g. So you would feel 0, right? So the next concept is, at the top, you feel or measure, right? You feel or measure whatever the ride is doing minus 1g. Okay? At the top, you feel or measure whatever the ride is doing minus a g. Which means, of course, at the bottom, what are you going to feel?
2G.
Yeah, you're going to feel 2 g's, right? The ride, well, actually, you're going to feel the ride plus a g, right? Whatever the ride is doing plus 1g at the bottom. And why is that? Well, because you've got a centrifugal force down of 1g if the ride is doing 1g, right? And then you've got gravity, which is also down 1g. So in general, you feel heavier at the bottom, you feel lighter at the top. And this is what we do at Oaks Park. We make these little gravity sensors. They're very sophisticated. I can't even begin to explain how complex they are, okay? They're not just clear plastic tubes with springs and masses, although you could do that, okay? They're vastly complex, and what we'll do is we'll actually use them to measure the g-force. From the perceived g-force, we can derive what the ride is doing, right? And then from that, we can figure out tangential velocities and all this stuff, right? So that's a lot of what we do. So this is concept 0, is just this idea that when you're in a vertical circle, at the top you feel a bit less, a bit lighter. At the bottom you feel a bit heavier. 1g heavier, 1g lighter, okay? So 2 types of problems we can solve. Okay, the first one is we want to keep the water in the bucket. We want to keep the riders on the ride. We want to, when we spin it upside down, we don't want objects to fall off of it, right? So what is the minimum speed at the top for my bucket if the radius is 1.12 meters so that the cup doesn't fall off, right? So let's draw a little circle. Small circles are harder. That's a pretty good circle, not a great one though. Okay? Okay, so at the top, what's the rule? If we want the water to stay in the bucket, we have to have an acceleration of at least 9.81, right? So what I'm going to do is I'm going to say A is v squared over r, right? So I'm going to say 9.81 is v squared over 1.12. V is the square root of 9.81, right? I kind of like this. This is like, it's always the square root of A times R. It's the pirate equation. R. Yeah? So this is, it's the absolute value, but we're talking about the speed here, so it's not really an issue. Okay, so second square root 9.81. Okay, so 3.31, how many sig figs do we have? 3 sig figs. V is equal to 3.31 meters per second. So presumably, if we go 3.31 meters per second, and this string really is 1.12 meters long, if we're going that fast, exactly that fast, then the string